Welcome to Group 12's presentation, the University of Virginia's School of Data Sciences Disaster Relief Project, in fulfillment of the requirements for the DS 6030 Statistical Learning class. Group 12 consists of Rian Ampoyo, Kamisha Bell, Delilah Cuevas Rodriguez, and Carmen Tran. Introduction. On January 12, 2010, a magnitude 7 earthquake hit Haiti, devastating Port-au-Prince. Approximately 230,000 people were killed, 300,000 injured, and 1.5 million displaced. Critical infrastructure was destroyed. Humanitarian aid agencies faced major operational challenges due to destroyed communication systems and roads. These hampered relief delivery. Rochester Institute of Technology, also known as RIT, teams collected geo-referenced images using aerial photography. The imagery revealed that displaced individuals whose homes were destroyed were using blue tarps to construct temporary shelters. Manually locating blue tarps among thousands of images was infeasible. The solution to this challenge was to use data mining algorithms. So statistical learning algorithms were employed for efficient identification of people in need of assistance. Group 12's project goal is to use methods learned in UVA's Data Science 6030 course to build and evaluate multiple models to optimize displaced person detection. Exploratory data analysis. We will suspend discussion of the basic attributes of the dense training and holdout data sets provided for this exercise, move directly into talking about core features of the data used to identify the blue tarps in the aforementioned RIT images. To determine the location of blue tarps in the images, Group 12 transformed the class response variable into a bivariate output. The new variable was assigned a value of blue tarp for observations with the class of blue tarp, with all of the other 4 values coded as not blue tarp. The blue tarp values accounted for about 3% of the training data set. T-tests indicate that all 3 features, red, green, and blue, have statistically significant differences between the binary blue tarp classes. After this transformation, the color values remain highly effective in distinguishing between the categories as displayed in this 3D scatter plot. The holdout data set was comprised of 8 individual text and 3 JPEG image files. The holdout data set, which contains more than 2 million observations, also includes a categorical variable called class. Like the training data set, this data did not contain any missing values. Unlike the training data set, this variable already classified the data as either blue tarp, which represented about 1% of the data, or not blue tarp. Therefore, no further transformations were needed. After exploring all possible RGB color combinations using an RGB calculator, we determined that interpreting column 8, B1 as red, column 9, B2 as green, and column 10, column B3 as blue, produced scatter plots with colors that closely matched those provided in the examples. The other 5 permutations resulted in unnatural hues of green, purple, or turquoise, indicating an incorrect mapping of the color channels. It is important to note that the position of the figures in the plot was not a factor in our analysis. This approach was solely used to verify the correct order of the RGB values, as shown in this scatter plot that is highlighted on the screen. After data preparation Including applying factors to the class output variable, the team was ready to proceed with its analysis.
Now I will be discussing on our description of our methodology that we used for this project. And this is going to be a little overview on the methodology. For this project, we used R as our primary tool, specifically leveraging the Tiny Models framework. This allowed us to create a modular and reproducible workflow, making it easier to manage pre-processing, modeling, and evaluation steps consistently across models. To document our work and collaborate effectively, we used Microsoft Word for the final report. Our modeling task was framed as a supervised classification problem with the goal of predicting the presence of blue tarps in aerial imagery following a disaster. And as you can see in this visual, our pipeline moves systematically from data preparation through evaluation, ensuring that each phase was well-defined and repeatable. Now on to model development and validation strategy. To train and validate our models, we applied tenfold stratified cross-validation to the training data. This method was chosen because our dataset was imbalanced, meaning the blue tarp class was underrepresented. Stratification helped ensure that each fold preserved the class proportions, reducing bias and improving the model's ability to generalize. After cross-validation, we evaluated final model performance using a holdout test set, which was never seen during training. We also optimized the classification threshold based on the ROC curve in AUC, which I'll explain further in the next slide. When selecting our threshold, the classification threshold played a critical role in how our model balanced between sensitivity and specificity. To determine the best threshold, we examined the ROC curve and calculated the area under the curve, or AUC. We looked for a point on the curve that gave us a strong true positive rate while keeping the false positive rate low. And based on this analysis, we selected a threshold of 0.7, which offered the best trade-off for most of our models. This choice helped us reduce false positives, which is especially important in disaster response scenarios, where misidentification could lead to wasted resources. Now for our model evaluation metrics. To comprehensively evaluate model performance, we relied on a range of metrics, and as you can see on our first bullet point, we had accuracy, which gave us a baseline idea of how often the model was correct. But because our data set is imbalanced, we also used the Breyer score, and this was to evaluate the quality of probability predictions. We also used AUC and ROC to measure how well the model distinguishes between classes. Precision was key for minimizing false positives and true positive rate, or recall. And this helped us ensure we didn't miss actual cases of blue tarps. We also tracked false positive rate to keep an eye on how many negative cases were incorrectly flagged. And altogether, these metrics gave us a well-rounded view of how our models would perform in real-world conditions. And I decided to include a picture, well, not related to our actual project. I felt like it was a good example on true positive and false positives. And here we can see how the cat disguised as a dog appeared to be a false positive when classifying what could be a dog in images, and while not as serious as what was at stake in our project, having precision is very important when classifying what is actually a blue tarp, because as mentioned before, it could lead to wasted resources and not being able to efficiently help those in need.
Before diving into the results, it's important to know how we quantified the performance of each model. We looked at metrics such as ROC AUC, accuracy, sensitivity, and specificity. We ended up choosing to use sensitivity as our main metric in measuring each model's performance. This is due to the concept of class imbalance. There were far many labels for non-blue tarps than there were for blue tarps. Therefore, it wouldn't have been appropriate for us to settle on accuracy or ROC AUC as our metric. Hence why we looked into sensitivity, which shows us our model's efficacy on detecting true positives. We mentioned earlier that we wanted to maximize our true positive rates due to the nature of the data. Remember, we're looking to find survivors of the earthquake who resided in blue tarps, so it's important that we choose our models to have high true positive rates so that we don't misclassify blue tarps in the given photos. Also, all models are tuned, if possible, to their optimal tuning parameters, ensuring that each model performed at their best for this dataset. Here is a visualization comparing the ROC curves of all the models, which gives a general idea of how well a classification model performs. Here, we can see that there are two models that do not perform as well as the others according to the ROC curve, which are the k-nearest neighbor models and the linear discriminant model. It should be noted that even though these two models don't perform as well as the others, all of the models still do relatively well, as any ROC AUC score above 0.8 is generally considered good. We'll go more in depth about each model's ROC AUC scores in the next slide. Here's an easier visual for the numerical values of the ROC AUC scores. We can see more definitively that the k-nearest neighbor and linear discriminant models have the lowest scores. This is not to say that the models are bad, but rather the k-nearest neighbor and linear discriminant models did not perform as well as the other 5 models we trained. The ROC curve is a visual representation of the trade-off between sensitivity and specificity of a model. More on what this means for the results. The ROC AUC score measures how well a model can produce relative scores to discriminate between positive or negative instances across all classification thresholds, in this case, blue tarp and non-blue tarp labels. It's also important to note that the plot has its y-axis restricted to a limit of 0.97 to 1 to make it easier to see the very small differences of ROC AUC scores of each model. All of these models are tuned for their optimal parameters, so each of these models should be the best version of themselves for this specific data set. After tuning, if we were using ROC AUC as our metric to choose the best model, it turns out that the random forest model performed the best in regard to this data set. Recall in the last slide, I stated it's important that we choose our models to have high true positive rates so that we don't misclassify blue tarps in the given photos. In other words, we want to choose the model that had the highest sensitivity, so our chosen model has the most correctly classified labels for blue tarps. However, this comes at a cost, as I also mentioned that the ROC curve represents the trade-off between the sensitivity and specificity of a classifier model. So, we are not just choosing the model with the best sensitivity for free per se. We are instead trading how well a model classifies our true negatives. In this case, we don't really care about true negatives as much as the true positives for this dataset. Remember, we are trying to locate where the blue tarps are in order to save the lives of earthquake victims. We're not too concerned about the areas that don't have blue tarps. While yes, in context, this may cost us money and resources, but that's a conversation for another time. With this in mind, we look to choosing the model with the highest sensitivity. Even though this model had one of the lower ROC AUC scores, the k-nearest neighbor model turns out to have the highest sensitivity.
Now let's move on to the conclusion. So, for conclusion 1, logistic regression outperforms LDA and QDA. Finally, we found that logistic regression, while often considered a simpler model, actually outperforms more complex ones like QDA and LDA on the holdout data. Its low false positive rate and near perfect precision make it ideal for reliable tarp identification. And by introducing regularization or even ensemble enhancement, we can make it even more robust and adapted to a varying condition and data source. Conclusion 2, enhance logistic regression with regularization and ensemble model. To further enhance the performance of logistic regression, which already outperform other models on the holdout data set, we recommend a few key improvements. First, incorporating regularization techniques like L1 or L2 penalties can help reduce overfitting and improve generalization, especially in varying lighting conditions that affect color data. Second, ensemble methods such as random forest or boosting could be explored to capture more complex patterns and improve overall robustness. We also suggest leveraging spatial and geospatial features such as map coordinates to boost clarification accuracy and uncover potential clustering in tarp location. Lastly, fine-tuning the model's probability threshold could help increase true positive detections without significantly raising false positive. Conclusion 3. K-nearest neighbor performs best using cross-validation and the holdout data. Let's start by looking at the performance across different evaluation phases. During cross-validation, the K-nearest neighbor model performed the best in terms of sensitivity, with a mean score about 96%. This means it was the most successful at identifying true positive cases, which is especially important for tasks like detecting blue tarps, where missing a real tarp could be costly. On the other hand, the random forest model had the highest ROC AUC score, just under 1, indicating outstanding ability to separate classes overall. While it didn't outperform K-nearest neighbor in sensitivity, its high AUC suggests it might be generalized better when applied to new unseen data, potentially making it a more stable performer on holdout data. Conclusion 4. The findings between cross-validation and holdout is reconcilable outcome. The K-nearest neighbor excels in sensitivity, meaning its aggressiveness captures all true positives, but it can be prone to overfitting, especially with smaller data sets. This might inflate its cross-validation scores without translating as well to the holdout performance. In contrast, random forest leverages ensemble learning, making it more stable and generalizable. Its AUC score reflects this strength in broad classification performance. So even though each model excels a different metric, they're both doing exactly what they're built to do, and their performance is consistent with their design. Conclusion 5. K-nearest neighbor model should be used for the detection of blue tarps. Now let's talk more about which model we'd actually recommend for blue tarp detection. In this scenario, we care most about sensitivity catching every possible instance of blue tarp. Missing one could mean overlooking a location that needs emergency aid or disaster response. Given that, the K-nearest neighbor model with the K set to 16 is our top pick. It may not be the most balanced model overall, but it is the best at what matters here, not missing a positive case. In this context, a few false alarms are okay, missing an actual tarp is not. Conclusion 6. Accuracy, ROC, AUC, sensitivity, and specificity are essential to blue tarp detection. The metric we used, accuracy, sensitivity, and specificity, and ROC, AUC, are highly relevant to this context. Sensitivity ensures that we don't miss actual tarps. Specificity prevents false alarm. ROC, AUC helps us assess overall discrimination ability. These aren't just academic measures. They directly impact life-saving decisions in high-pressure environments, guiding where emergency aid goes and when. In conclusion, our analysis shows the importance of model evaluation across multiple dimensions. Whether it's through generalization, interpretability, or real-world readiness, our goal remains the same: to build tools that help save lives quickly and accuracy. Thank you for listening to our presentation.